In this video, we're going to discuss the logistic regression algorithm. Specifically, we're going to see how we can formulate the logistic regression problem, what is the motivation for our formulation, and how we can solve the logistic regression algorithm. So the linear models that we have seen so far are two types of models. We have seen a linear classification example via the linear perceptron algorithm and the linear regression model. So as part of the linear perceptron algorithm, we said that we use this linear combination of our input features. Each of our input features is multiplied by a weight, and we also have a bias term. And we learn the weights for the algorithm such that the samples that belong to the positive class are on one side of the hyperplane, and the samples that belong to the negative class can lie on the other side of the hyperplane. And the weights are being learned in order to find a hyperplane that actually performs this classification. Now, when we go to our linear regression model, again, we multiply our input features by a set of weights. However, instead of looking at the sign of this expression, we are actually hypothesizing that the outcome equals to the multiplication of our input features with each of the weights. And basically, the linear regression model results in a continuous outcome. The linear classification through the linear perceptron model results in a binary outcome. And we have also seen the multi-class case for the linear perceptron algorithm. Now, the logistic regression, while the name has the term regression in it, is actually a classification algorithm, and it will assume that instead of having this sign function that basically performs a hard assignment of each sample to either a positive or a negative class, the outcome of logistic regression will be a probability, and it will perform this soft assignment of an input sample to a probability that corresponds to how likely it is that the given sample belongs to the positive class. And the good thing about that is that through the logistic regression, we can actually model uncertainty. So this is an example of how our credit analysis application would work in the case of these three algorithms that we discussed. If we had a linear perceptron algorithm, our algorithm would either approve or deny credit to an individual. If we have a linear regression algorithm, this would estimate the amount of credit that we can grant to an individual. And in the logistic regression case, we're going to estimate the probability of approving a credit for an individual. And one function that's going to be actually very useful when we discuss the logistic regression is the sigmoid function. And the reason is that, as we said, this term of linear combination of weights, W transpose T, is a very useful and important term because essentially it allows us to transform our input sample via some weights into a single expression. However, the value W transpose X ranges from -infinity to infinity. Now, if we are to try to assign a probability to this value, then this probability output should be between 0 and 1. And the sigmoid function has the ability to map an input number that ranges from -infinity to infinity into an output that ranges from 0 to 1. This is a definition of the sigmoid function, and this is how the sigmoid function can be plotted. So we can see again that when our input is 0, then the probability of the output of that sigmoid function is at 0.5. When our input is less than 0, then the output is lower than 0.5, between 0 and 0.5. And when the input is larger than 0, then the output is between 0.5 and 1. And because now our output is bounded between 0 and 1, it can be interpreted as a probability, which is the goal for the logistic regression model. The fact that also this sigmoid function is monotonically increasing, it makes it a very attractive function for this to be used for classification rules. And finally, another advantage of this sigmoid function is that mathematically we can handle it in a very easy way to perform our optimization. So to give a brief overview of logistic regression is a parametric classifier. And as part of this classification process, we still compute a linear combination of our features. This linear combination is always expressed as this inner product between a weight vector and our input vector. But now, instead of predicting a continuous output from this W transpose X, or instead of applying the sign rule so that we can see whether this W transpose X is greater or less than 0, we pass this inner product through the sigmoid function. Again, this inner product can range between minus infinity and plus infinity, but by passing this through the sigmoid function, we make the outcome of this sigmoid W transpose X to be between 0 and 1. And therefore, it can be interpreted as a probability. So if we go back to the Bernoulli distribution that we discussed as part of the previous video, the Bernoulli distribution simulates a binary process in which we either select class 1 or class 0 with a probability parameter theta. The parameter theta is the probability of choosing class 1. Now, instead of using a random parameter theta as the probability of choosing class 1, we can actually use this sigmoid of W transpose X. The W transpose X essentially represents a linear combination of our input space. And through this sigma function, this linear combination of our input features is being passed, is being transformed into a probability. Therefore, this probability can be a very appropriate fit for being the parameter of our Bernoulli distribution. Now, if our output X belongs to class 1, we can say that this occurs with a probability sigmoid of W transpose X. And if our sample belongs to class 0, then this occurs with a probability 1 minus sigma of W transpose X. So if we were to formally define our linear regression algorithm, we would have, again, an input of features. We would have an output. In this case, we only are limited to the binary classification output for now. And we also have a set of training data from n samples. Now, the model takes us from an input space X to the output space Y by expressing the probability of our output belonging to class 1, given our features and the weights of the logistic regression model. And this probability is actually equal to this sigmoid of W transpose X. As part of the decision rule, if we can assume that we can have a threshold of 0.5, if we want to actually assign a class to our input sample. So for example, if this probability is greater than 0.5, we can assign the sample to belong to class 1. Otherwise, we can assign the sample to class 0. And given that we have a set of training data, now the model parameters that we need to find are again the weights of our model, the weights with which we multiply our input space. Another example that we can that we can exemplify the logistic regression model is to model the probability of whether a student would pass or not a class based on their SAT scores. So on the x-axis here, we can see the SAT scores of multiple students, and on the y-axis we can see the probability of a student passing the class. Now, based on this logistic regression model, if we have a 0.5 threshold, we can see that whichever students have SAT scores that correspond to this 0.5 threshold, which is mapped to an SAT score of 540, this will pass the class based on these logistic regression models, and the rest would not pass the class. Now, as we discussed, the unknown variable of logistic regression is the weight with which we multiply our input samples. And we need to find some type of optimization function in order to find this weight. Now, an optimization function that would be a very good fit for this type of problem would be some type of likelihood estimation, and especially a maximum likelihood estimation. And the reason for that is that now we are operating on the probability space. We have assumed a probabilistic form of a model. So we have assumed that a training sample belongs to class 1 with this probability, which is reflected by the sigmoid function. A training sample belongs to class 0 with 1 minus the sigmoid function of W transpose X. Therefore, we would like to find the set of weights that maximizes the data likelihood for all our training data. If you remember what we had discussed about the Bernoulli distribution, is that if an output variable, in this case, the probability of our training sample, in this case, our training sample N belonging to class 1 has a binary outcome, and the probability of a class, of the positive class, is represented by a parameter theta. In this case, this parameter theta is this entire sigmoid function. Then actually we have an expression from the Bernoulli distribution, and that expression is that. So essentially, this expression and the expression that is being shown here are exactly equivalent. This is the likelihood for one training sample. How can we find the likelihood for all our training data? We just multiply the separate likelihoods for each training sample. So essentially what we do is that we just put a product here that ranges between 1 and n. And again, we have this entire expression of each of the separate likelihoods for each of our training samples. Instead of trying to maximize this data likelihood, which computationally can be very expensive because we have these exponential terms here, what we can do is we can maximize the log likelihood or minimize the negative log likelihood. The negative log likelihood is referred to as cross-entropy error, and this is what we are going to actually minimize. So essentially, the cross-entropy error, by definition, is equal to the negative sign of the log likelihood of our data. Now, if we apply the logarithm in this expression, then this expression becomes like that. So what we need to do is that we need to minimize this expression in terms of W. Based on what we have discussed so far, how can we minimize an optimization criterion? We can find its first order derivative in case actually this first order derivative exists. So in this case, the first order derivative of this cross-entropy error exists. However, we cannot find a closed form solution, which means that if we set the first order derivative of this cross-entropy error to 0, then it will not have a closed form solution. For this reason, we are going to apply an approximate method, and we can actually very easily apply the gradient descent method. So all we need to do is find the first order derivative of this cross-entropy error and just plug this first order derivative into the gradient descent update. And then we can find the weights of our logistic regression model by iteratively updating this weight based on the first order derivative of the cross-entropy error. So next, we are going to derive this first order derivative, which we are going to see that this is the actual computation of the first order derivative. And we are also going to show some details on how this cross-entropy error is actually a convex function. So this derivation, in which our goal is to compute the first order derivative of the cross-entropy function for the linear regression, we're going to start by computing the first order derivative of a sigmoid function. And the reason for that is that this will be very handful when we're going to compute the first order derivative of the cross-entropy error. So if we have a sigmoid function, which is defined by this formula here, then the first order derivative of this, if we apply the chain rule, is going to be minus 1 over the denominator of this raised to the power of 2. And then we also need to find the first order derivative of the denominator, which is minus e to the power of minus n. Now, if we keep analyzing this expression, what we can do is that we can bring this term, which corresponds to sigma of n, on one side of the expression, and this other term on the other side of the expression. But what we can see is that this term actually corresponds to 1 minus sigma of n. Therefore, the first order derivative of sigma of n with respect to n is equal to sigma of n times 1 minus sigma of n. So we're going to use this derivation in order to compute the first order derivative of the cross-entropy error. And let's go now to the point where we have actually found the cross-entropy error. What we're going to do is that we are going to apply the chain rule here in order to find the first order derivative of this with respect to W. And in this chain rule, we are also going to take advantage of the derivation that we just did. So first things first, because this is a sum, these derivatives can be independently computed for each of the samples xn. And let's start by computing the first order derivative of this expression with respect to W. We can see that this term is just a multiplier, so this term can stay here. Now we have the logarithm of an expression that depends on W, so this would be 1 over that expression. However, because we have a function that depends on W, we need to apply the chain rule and also multiply what we have so far by the first order derivative of this function with respect to W. So the first order derivative of a function sigma of n, we have shown that it is the product of sigma of n multiplied by 1 minus sigma of n. However, we also now need to apply one more nested chain rule here, just because whatever is inside this sigma function does not depend solely on W, but it is another function of W. Therefore, we have to multiply this entire expression by the first order derivative of this smaller expression with respect to W, which is just this term x of n. So far, we have computed this first order derivative of the first term of the sum. Very similarly, we can compute the first order derivative of the second term. Again, 1 minus yn is just the multiplier here, does not depend on W, so it can stay the same. The derivative of the logarithm of this entire expression is 1 over whatever is inside the logarithm. Now we need to apply the chain rule to compute the first order derivative of this function here. By the first order derivative of sigma of n. This is 1 minus sigma of n, which is essentially sigma of n, and then 1 minus the 1 minus sigma of n. This thing here and this thing here have been derived in exactly the same way. The main difference is that here sigma of n is this sigma of W transpose xn. When we apply the same rule here, then sigma of n is this entire thing. And finally, what we need to do is again find the first order derivative of this entire expression with respect to of this entire expression with respect to W, which is minus x of n. So after having computed this entire thing, we can just simplify this expression. So this term here and this term here cancel each other. This term here and this term here also cancel each other. And once we further keep simplifying this expression, this is going to result in this final sum here. So you can see that in this final sum, basically the gradient of the cross-entropy error depends on the difference between the predicted probability from the actual label of each training sample. And this is again some type of error. So when we apply gradient descent, this means that the samples that are going to be far away from their true labels when we use the current value of weight W are going to contribute more to the gradient descent rule. In contrast, the samples for whom the likelihood is very close to the true label are going to contribute less to this gradient descent rule. Now, another thing that we can show here is that the Hessian of the cross-entropy error is positive definite. We can compute the Hessian by just computing the first order derivative of the gradient of the cross-entropy error. By definition now, this is the gradient of the cross-entropy error, and we just compute one more time its first order derivative. Once we do all the calculations, again using the chain rule, we are going to find that the Hessian of the cross-entropy error is equal to this expression here. So in this expression, these terms sigma and 1 minus sigma are just real numbers. And because sigma is always between 0 and 1 minus sigma is always going to be between 0 and 1. Therefore, this entire product is going to be positive and between 0 and 1. So all we need to show here is that this matrix, which results from the multiplication, the multiplication of each input sample, is positive definite. Again, this is not an inner product because it's not x transpose times x. The result of this is a matrix because the dimensionality of a single sample xn is d times 1. The dimensionality of its transpose is 1 times d. Therefore, the multiplication of these two results in a d by d matrix. So we need to show that this d by d matrix is positive semi-definite. In order to do that, we can use the theorem that we had described in one of our previous classes. So in order to show that any matrix is positive semi-definite, we need for all vectors v that have the same dimension as one of the two dimensions of the matrix, we need this expression to be greater or equal to 0. So what we do is we substitute basically this thing here. The multiplication of sigma times 1 minus sigma can be just represented by a single number here, just to simplify visually this expression. So therefore, this thing results into this expression here. What we can do is that we can bring V transpose and V inside the sum. And after we do so, we have basically X transpose V and its transpose multiplied by itself. Now, a vector multiplied by itself is actually the L2 norm of that vector. The L2 norm is always positive. Therefore, this product will be positive because mu is also positive. Therefore, this entire sum is going to be positive. This is the end of the video that describes the binary classification using the logistic regression algorithm. And in the next video, we're going to demonstrate the multi-class classification example.